Okay, good afternoon, everyone. Welcome to the Provost lecture series. This is the second one. The first one was given by Professor Ichiro Maruyama 2 weeks ago, and who just retired. And he was able to give a really nice lecture. He invited his wife, and his talk will be posted online very soon, in a couple of days. And Scotty already created a YouTube link. And for those of you who are here for the first time, so this is one of the initiatives the Provost office started this October. And the purpose for the Provost lecture series is to celebrate milestones in the careers for OIST faculty members, those who are going to retire and those who get promoted. So for today's lecture given by Professor Mahesh Bandi, so he's recently promoted to full professor. And again, I would like to show this slide as a thank you note. And some of you are not shown here, such as Scotty, several people from the CPR. They have been very helpful in terms of designing the posters and related to the video recordings, writing the story, and so on. And also a big thank you to the staff members from the Provost office, and in particular, Matsukawa-san and also Magai-san, who have been working very hard to make this possible. And also Patrick Kennedy, who's tasked to make our special gift also possible by doing 3D printing. And also everybody showing here, so without their support and approval, it's not possible to make the Provost lecture series. So thank you again. And again, so now me being also the Provost, I understand there are a lot of approvals and we have to get up very early every day to go through all the approvals. And it's very necessary. And so this is the gift to Mahesh. And so all the details are taken care of in terms of what's written. And this is courtesy by Peter. And also the font, type, and size, everything. I hope you like it. And so finally, I would like to introduce President Peter Gruss, who is going to introduce Mahesh Bandi. I asked Peter to provide a nice photo. And as you can see, Peter is very ready to celebrate Christmas and the holiday season. And so after the lecture, so we will serve some coffee and snacks in the patio area. Again, please be very mindful. So when you talk to your colleagues and so on, so we can prevent the COVID-19 spread. So now the floor is all yours, Peter.
Yes, so what you saw is a preview for the upcoming holidays. I'm already getting warmed up here. No, I don't need anything. No.
Okay.
So in any case, I thank you very much, Amy, and I'd like to start by expressing my gratitude to you for setting up the Provost lecture, because I believe this was a missing link. It complements the many specific talks we have that are for very distinct audiences, and it allows everybody, including admin actually, to hopefully understand and take home something about what OIST research is all about. Now, today's speaker is Mahesh Bandi. And Mahesh doesn't really need an introduction because he's one of the founding faculty members who has joined OIST even before OIST was an accredited university in 2011. Mahesh studied at the University of Pittsburgh, where he also received his PhD in physics. He was a postdoctoral researcher at Los Alamos and Harvard. And after being a visiting faculty at Brown University, He joined OIST as an assistant professor, being promoted to tenured associate professor in 2018. Now, as Amy indicated, we are actually lucky that we still have Mahesh. He recently received an impressive offer, and thanks to an extraordinary effort by our BOG and by our management, we could promote him to full professor and extended a counter offer that he accepted. Thank you, Mahesh. You will not regret it, I hope. Of course, we solicited the opinion of leading physicists. Here is just one statement strongly supporting our retention efforts that I want to share with you. I quote, "He's an outstanding creative scientist with wide curiosity and inborn talent for experimentation. World-class soft condensed matter experimentalist, combining sophisticated technical abilities with outstanding intuition and understanding of theoretical and conceptual issues in a class of his own." Still a quote. Mahesh has also a keen sense of humor. He often jokes that he works in doesn't matter physics, as it chimes with condensed matter physics. More seriously, he sees physics as the art of approximation that provides a general bag of tools to think about many things beyond the field's core questions. But, and this was also quite clear in the past 3-4 years, he doesn't sit in a theoretical ivory tower. When face masks, the N95 respirators, were unavailable during the early days of the COVID-19 pandemic, he built a cotton candy machine in his garage and manufactured electrocharged non-woven polymer fabrics with commonly available material such as a drill and discarded plastic bottle caps. After validating the material and confirming the filtration efficiency that it meets the NIOSH N95 standard, he kept essential healthcare workers in Okinawa supplied with N95 respirators until the commercial ones became available. Where many of us would have had our plates full with one research area, he moves easily among a wide spectrum of problems, such as the spectrum of wind power fluctuation or the stiffness of the human foot and evolution of the transverse arch. Well, there is something like that in anatomy. We all need it, and we use it actually heavily. His scope and his energy are humongous, which enabled him to also provide invaluable assistance to numerous non-governmental and governmental agencies. I personally benefited from his advice on our COVID-19 emergency response, which has helped to make the right decisions during the entire COVID-19 pandemic and kept OIST on a clean course without a major breakout of COVID-19, not the least thanks to Mahesh Bandi. So, without further ado, let's hear Mahesh if, as a wanderer, he ever got lost.
Thank you so much. Thank you, Peter, for your very generous introduction. It's an honor and a pleasure. This is my second invited talk at OIST and in the same auditorium. My first invited talk was here a little over 10 years ago. It was my job talk. So, why these masks, these Venetian face masks? they have something to do with the fact that they all come from the Venetian Carnival in 2020. But I'm going to try and weave a non-linear story involving Venice as the central point in space across various points in time. So, moving forward, so the date is February 22nd, 2020. I'm outside the Santa Lucia station in Venezia. These are the videos I took that morning. All the crowds out there. I was there to catch a train to Trieste to teach at the Spring College on Physics of Complex Systems to start 24th February. I was one of the 4 lecturers at that school. And there was nothing out of the ordinary that morning, except for the fact that there were members of the Italian Armed Forces with IR temperature sensors at the airport as I was disembarking. And I bought my train ticket and I continued to get my photos. Here is one photo of a lady and a gentleman. These are the last few days of the Venetian Carnival. And on February 23rd, the carnival was closed down as Italy went into lockdown and the school was cancelled. I finally left Italy on February 28th and made it back to Japan. So during those few days, while I was recording my video lectures at ICTP, it was also the first time I had ever heard of the N95 masks, and I did not know anything about them. Meanwhile, in Japan, apart from the fact that the Japanese yen was 109 yen to the US dollar, masks were getting pretty difficult to find. Here is a DIY Doraemon mask. This was from Feb 25th, 2020. And as I said, I had never heard of N95 faceless respirators before. So late Feb, while in Trieste, I started reading about N95 for the first time in media. Then I started looking up the literature. And I come back to Japan. It was a breeze through the airport, no questions asked. I came home and I chose to self-isolate for 2 weeks. And during that period, I asked myself, how does an N95 filter more than 95% of the particles, and can I make one? And one of the first sources I found was this document from the National Academy's press, the National Academy of Sciences of the United States. And this image, this schematic is taken from their book, which basically explains that there is no one-shot solution to filtration of these bioaerosol particles. And you have to apply a range of strategies. One is that if you have particles that are 10 microns or larger in size, then they don't follow the streamlines of the flow, of the airflow, so they go and slam into the filtration layers, and they get stuck. Second is when particles are so small that they can diffuse away from the streamlines and then get stuck to the fiber. And the third is through electrostatic attraction. Since I'm not good at this, I have actually borrowed an instructive video.
And upon learning about them, you might think, like I did, that an N95 mask is basically a really, really fine strainer, a mesh of fibers with gaps too small for dust and other airborne particles to get through. A strainer filters out particles larger than its openings, but not particles smaller than its openings. So you'd expect that with a mask, after a certain point, small enough particles will sneak through. But this isn't how N95 masks work. The particles they filter are generally much smaller than the gaps between the fibers in the mask. What's more, an N95 mask is actually really good at filtering both the largest and smallest small particles. It's medium-sized small particles that are hardest for it to block. This isn't at all like a strainer, because N95s are much cleverer than strainers. The overarching goal of an N95 mask is instead to get an airborne particle to touch a fiber in the mask. Regardless of how big an airborne particle is, once it touches a fiber, it stays stuck to it and doesn't become airborne again. This isn't anything special about the fibers, but about the size of the particles. At a microscopic scale, everything is sticky, because the weakly attractive force between molecules is more than strong enough to hold very, very small things in place. So you shouldn't think of N95 masks like a fine window screen that keeps insects of a certain size out. You should think of them more like a sticky spider web that can catch an insect of any size, as long as it touches a strand. And so N95 masks use a bunch of different clever physics and mechanical tricks to get particles to touch their fibers. First, many spider webs are better than one. Unlike strainers, where stacking many identical ones doesn't improve the filtering at all, more layers of sticky fibers means more chances for particles to get stuck. And how likely particles are to hit or miss a fiber depends in large part on their size. Airborne particles larger than 1/1000th of a millimeter basically travel in straight lines because of their inertia. And because there are so many layers of fibers, their straight line paths are essentially guaranteed to hit a fiber and stick. Airborne particles that are really, really small are so light that collisions with air molecules literally bounce them around, so they move in a random zigzag pattern known as Brownian motion. This zigzagging also makes it super likely that a particle will bump into a fiber and get stuck. Particles of in-between sizes are the hardest to filter. That's because they don't travel in straight lines, and they also don't bounce around randomly. Instead, they're carried along with the air as it flows around fibers, meaning they're likely to get carried past fibers and sneak through even a mask with many layers. But N95 masks have a final trick up their sleeve. They can attract particles of all sizes to them using an electric field. In the presence of an electric field, even neutral particles develop an internal electrical imbalance which attracts them to the source of the field. This is why neutrally charged styrofoam sticks to a cat whose fur has been charged with static electricity. But unlike a cat's fur, an N95 mask's electric field isn't just ordinary static electricity. The fibers are like permanent magnets, but for electricity, electrets. Just like you can permanently magnetize a piece of iron by putting it in a strong enough magnetic field, you can electritize a piece of plastic to give it a permanent electric field. By electritizing the fibers in an N95 mask, they gain a long-lasting ability to attract particles, which means they capture about 10 times as many particles as regular fibers. And this is, after all, the point of an N95 mask, to filter out particles from the air, and they do it cleverly. By taking advantage of the molecular scale stickiness of matter, using many layers of fibers that catch straight-moving large particles as well as zigzagging small particles, and having an electric field that attracts all particles, you get a mask, not a strainer, that's really good at trapping both large and small airborne particles, and does a reasonably good job at filtering out middle-sized airborne particles. Precisely what fraction of those sneaky medium-sized particles get blocked gives you the number of the mask. If at least 95% of those particles are filtered out, then the mask is rated N95.
I'm sure all of us are now experts in N95 masks. We did not need this video. So, what is the usual way to manufacture these electret fabrics? One is electrospinning, where you have a polymer melt or a polymer that has been dissolved in an organic solvent, and you apply a high voltage field between the syringe, which we call the emitter, and the board here, which we call the collector, and by applying force on the piston, basically the pressure, that creates the creation of the droplets and leads to, and the electric field basically spins the fibers away, as you see here. This has a problem. Whereas this method is agnostic to the type of polymer, it has low throughput, so it will scale with the number of syringes. So if I want to make large number of fabrics, I need many syringes. Also, dealing with high voltage DC fields needs expertise in safety measures. The second, the industrial method, is called melt blowing, where you have a polymer melt that is sent down this knife edge, and you create an air knife where you blow hot air and it gets sprayed onto a conveyor belt, and as you see here, and as the fibers cool down on the belt, they are electrocharged by a corona discharge treatment if necessary. Now, this one, it's the most common manufacturing method. It is inherently suited for volume manufacturing, but it is not suitable for construction with common parts, which was the main goal of what I intended to do. So I was sitting in self-isolation. So, and I happened to have an American neighbor who had a cotton candy machine. Don't ask me why. And he has 4 kids, so but a chance remark, a passing remark by my postdoctoral mentor at Harvard back in 2010, he mentioned making polymeric nanofibers using cotton candy machines. That led me to look up, well, if he said something, he must have published it, and I found those papers, and using that, he had worked out basically what is the threshold angular velocity of this cotton candy machine, and what would be the average radius given the material parameters and the design parameters. So this is not an exact relation, and I guarantee you this is only one of 2 slides with any equations, but you don't need much to understand this. Basically, you need 2 ingredients to create these fabrics. One is you have to create a drop of polymer, and that is the initiation of the jet, and the second is to stretch it until it cools down and forms a strand. So for the jet initiation, there is basically competition between 2 kinds of forces: the capillary force, which is dominated by surface tension, versus the centrifugal force, which is caused by the spinning of the emitter that is sitting here. So once the jet is initiated, since this is not a Newtonian fluid like water, it is a non-Newtonian fluid because it's polymeric, it starts stretching. So that is achieved through competition between the viscous forces, which try to stop the fluid from stretching, and the centrifugal force. So the advantage of this method is not only can you construct it with commonly available parts, you can also achieve both the jet initiation as well as the fiber formation by the same forcing method, which is the centrifugal forcing. So then the question is, what is the threshold angular velocity at which one must spin this emitter through which the polymer is ejected? So typically, as you see in this video here for cotton candy, you put the material inside the emitter drum in between, and it has plenty of holes, which we call orifice, and we select the orifice radius. So from basically balancing these forces, you get the minimum velocity, angular velocity at which you must spin this emitter in order to initiate the jet. And once you initiate the jet, given the distance between the emitter and the collector, what would be the average radius of the fibers that you get? These are order of magnitude estimates, they are not exact. So that's called scaling analysis or dimensional analysis. Now, translating these parameters to design, the material, as Peter pointed out, was basically bottle caps and CD cases, which is basically polypropylene and polystyrene polymer. I will skip the technical details of isostatic versus low crystallinity polypropylene. Basically, one is brittle and the other is ductile. PS is basically polystyrene. You want to use what is known as general purpose polystyrene, not the expanded polystyrene which you use as styrofoam for packaging. By the way, styrofoam is very good for making napalm, which I practiced as a high school kid back in India. By the end of summer, the neighbor's wall was missing, so that's a different story. So we use low crystallinity propylene and polystyrene mixtures in the temperature range, which is given from the handbook of chemistry, so you can just look it up. And then from the calculations, the jet initiation, we needed a threshold revolutions per minute of about 4,500 RPM, but it started working at around 2,450. So as I said, this is an order of magnitude estimate, it is not exact. It tells you some ballpark figure at which things work. So a simple electric drill would work. A Dremel tool can go up to 35,000 RPM, but that's an overkill. The emitter I used was soda cans. So you see here, that was the drill and that was a soda can. Beer cans work best, actually. And the orifice radius we chose was hundreds of microns. And this is from the lab. So there was my neighbor's cotton candy machine that got destroyed through R&D, which is not research and development, it's a research and destruction part. And then I switched to this and it worked. So that was the R&D with the research and development part. And once that happened and the supply chain logistics opened up again, we managed to get this, and with Kieran's help, we started doing it. Once we had these fabrics, it was basically a question of taking the fibers that were generated, that basically end up like this. And while they're still hot, we just sandwich them between 2 thick glass plates to create a sheet, and cut them into rectangular sheets. And we tried 2 methods. One was the standard surgical mask. You put the electrocharged layer in it and apply it to protect yourself. The second was, with Kieran's help, there's an open source design that we found online called the Montana mask, because the person who designed this and left the 3D designs online for free was from Montana. And you just put it in the holder, and you can stick some rubber bands here, elastic bands, and you have a respirator. So what about the structural properties? So Ishizu-san, who I hope is here, she helped me with scanning electron microscopes, micrographs of the fabrics. So this is the scanning electron micrograph of a commercial N95 electrocharged layer. So that was our baseline against which we were testing what we were creating in the garage and then later in the lab. This is from isotactic polypropylene. This is from a mix of this low crystallinity polypropylene and polystyrene mix. This is low crystallinity polypropylene alone, and this is polystyrene alone. What you see immediately is this one is no good. It looks too brittle. This is no good because it is too ductile. These two were okay. Now it was a question of, okay, how do these candidates perform relative to the commercial N95 electrocharged layer when it comes to the filtration performance. So we also measured the average radii for all these materials, and if this was the benchmark we were looking against, the isotactic and the propylene and polystyrene mixtures compared decently well, whereas the low crystalline polypropylene was too high, polystyrene was just way too high. Now the question of electrocharging. For this, I sacrificed my microwave oven. What you need to electrocharge the fabrics is basically, there are different ways. The one we chose is what is known as isothermal charging. What you do there is you take two electrodes and zap the air at very high voltage, and basically the electric field rips the electron apart from the atom and creates ions. And what you need for the fabrics is negatively charged, so you want negative ion wind traveling towards the fabric. And the design rule for this comes from 1889, Friedrich Paschen, who is better known in atomic spectra for the Paschen series. You know the Lyman series, the Balmer series, there's the Paschen series, that's the Paschen. And he showed through empirical evidence that for any given gas, the breakdown voltage, that is the voltage at which the atoms or molecules of the gas rip apart, is a function only of the pressure and the electrode gap. And that was the empirical relation he gave, which was later put down properly in theoretical form by John Townsend. And so here, P is the gas pressure, D is the electrode gap, which is, these are the things we care about. But in our case, we didn't have high pressure facilities or low pressure facilities. We were working at atmospheric pressure. So if you translate all this into a lumped parameter model, as we call, say in physics, at one atmosphere, you can lump all parameters and you get the breakdown voltage as the distance inter-electrode gap times 30,000 in centimeters. Okay. Now, for voltage above the breakdown voltage, you get what is known as an ionization region near the active electrode, and there is a space charge field. Now, this is a very nonlinear problem. Nobody has ever solved it accurately. There are very serious linearizations, and then you have a solution for very specific geometries, like the point plate and the point cylinder geometry, which gives you the voltage current characteristics. But I'm not lazy, I'm just an effort minimalist. I overcame that calculation by a circuit solution, which was take apart the microwave, you get the transformer, and you get a second transformer, which means a second microwave, and that's your 110 volt AC line, a switch. All of us understand that so far. One line goes to this ballast. This guy does something interesting. It acts as a safety catch. It doesn't let too much current pass through. And by doing so, I did not have to sit and calculate this nonlinear resistor problem, which would, the Russians haven't solved it, and if they haven't solved it, there's no hope for me. Right? And then you have the transformer, which cranks up the voltage, and it goes through what we call a diode bridge, which will convert the AC into a DC, and you get the voltage output in the electrodes. When you do that, now there is the electrode design part. The problem is I can't put the fabric in between the electrodes because the sparks will punch a hole through the fabric. So what we did was we put a fan to blow the air, so the sparks would go from the negative to the ground electrode, but the ions would be passed on to the fabric sample through a transverse jet. And it's basically a centrifugal fan taken from an old computer. I'm not telling you which one because it still has an asset tag. A 3D printer printed flow focusing and powder composite casing with these two electrodes. And when you play it, so that's a video, and you can hear the fast clicking. That's actually a sign that this is negative ions, that this is negative corona discharge. If it is positive, it's called streaming, and you don't hear these clicks. So once that is done, now we have to worry about optimal treatment. And what you're looking at here is infrared imaging of fabric masks being exposed to the ionic wind, which you can see like air blowing down. That is basically the ions coming down. So we had to do it at different distances from the mask, distances between the mask and the electrodes, because if the electrodes were too close, it would basically burn the fabric. The temperature would get so hot. You can see this one, in this case, the distance was less than 5 centimeters, and it was basically getting too hot, and so the polymer was melting once again. So you had to have an optimal distance where it wouldn't melt, but it would also transfer enough ions so that the fabric would get charged. So once we figured that out, then we come to the next problem, and this was done by, so this, for this work I was assisted by Pinaki's postdoc, Julio, I don't know if he's here, but he came to the lab and helped me do the imaging and figure out what was the problem. Now here, Scotty comes in, and we thought, okay, we will take a few videos for the OIST website, but it turned out the method I was following was wrong. You see some yellow flashes come through on occasion, and those yellow flashes are basically the flame from the sparks singeing the cloth and creating these pinhole burns. So if you have a pinhole burn that is roughly on the order of 10 microns, then no good, right? No N95. So we had to take care of that. And once we did all of that and nailed down the working parameters, now we come to the beautiful plots. This is the time when my late PhD advisor used to wake up from his sleep during talks. So what do we have here? The test had to run 12 hours because that is the typical time a healthcare worker would wear their mask. And what you're looking at is a brand new commercial N95 mask, which is over here. So that had between minus 10 and minus 12 nanocoulombs. So that was a baseline. If we were to take the mask, dip it in alcohol to get rid of all its charge, and then recharge it with electrocharging method with the homemade plasma apparatus, then we did almost as good, minus 10 nanocoulombs. Then comes polystyrene, which is almost as good, and then polypropylene, which is here, which is not so good, and then surgical masks are somewhere here. Now, not all surgical masks work because some are made of polycotton, and that does not electrocharge, but if they are made of polymer, then it works. And then we wondered, is it possible to take any cloth masks and charge them as well? This was just a shot in the dark. And it turned out you cannot. You can, but it's no good. So what happened was we started noticing that it would get charged, but over a period of time, it would decay, the charge would decay and settle to some value, and usually it would even go down to complete zero charge. So we wondered what that was, because this constant charge over 12-hour period, that told us these fabrics are electrics and isothermal charging was at work. And there's an established procedure for it in literature. But this one had never been worked out. It turns out the exposure of plasma to fabrics has been done in the textile industry to make them wrinkle-free or fire retardant, but not to see if they can attract charges. So we wondered what was happening there. And since I don't have the capacity to go to higher pressures, but we had a small vacuum pump and a bell jar, so we exposed the fabric to these ions at 2 different pressures and 2 different temperatures. Sorry, various pressures and 2 different temperatures. And what you see is, as a function of the pressure and temperature, the amount of charge uptake onto the cloth fabric changes. And this tells you that the amount of charge that is sticking onto the cloth, fabric cloth, is basically subject to some thermodynamic variables. Why? Because all of thermodynamics is based on temperature, pressure, and volume, right? So one more test to see if I could do this cycle. Basically, we start at point A, which is around 80 kilopascals at 23 degrees Celsius. Run down the temperature at the same pressure to point B, and then go to point C, where we are staying on the same temperature line, but we decrease the pressure to 60 kilopascals and go back up to D and then back to A. If you can repeat that cycle, then that tells you you're in an adsorption-desorption regime, which is subject to thermodynamic variables. So we only provided proof that the ions that are taken up by the fabrics are due to adsorption, but then the problem is adsorption and desorption are dominated by temperature. So if an individual wears a cloth mask that has been electrocharged by this method, there is hot air that is exhaled in our breath, so the desorption is actually going to get accelerated. So whereas we could not come up with a method or technique to electrocharge cloth-based masks directly, we were able to show that there is a method of adsorption and desorption working. We did not go any further because the theory of adsorption and desorption actually is not completed yet. So, and this work was not about that study. Finally, the proof of the pudding, test the filtration capacity. So, usual systems that test for the filtration efficiency come from a company called TSI in Minnesota for about $150,000 a machine. And this, not only did we not have that kind of money to throw, it was also a time when all the supply chain logistics were broken down. So we made one at home. So we purchased a mannequin head from Okinawa City. I took apart an ultrasonicator and pulled out its, what do you call it, the piezo drive, and you could generate steam, basically vapor from the sonication. So you generate the mist, you have an air intake, and then you have a flow rate valve to control the concentration of mist that is entering the chamber. You have a mannequin head, and this is one of the times when you feel the thrill of being a serial killer. You drill a head through the mannequin head from behind, you put a mask in the front, and now we did not have the special particle counters that I used in this trade because they come for $150,000 a pop. We used what I've used for an environmental monitoring. So we borrowed one from Buildings and Facilities Management, and I bought one more from Amazon. So one was inside to get the concentration inside the box, and the other outside. We stuck it to a vacuum pump. So one shortcoming of this test is it does not create the oscillatory back and forth flow that of inhalation and exhalation, but it's better than no test. So once we did that, let's look at the results. So for a commercial N95, so let me tell you what this means. So the quantity you want to look at is the penetration, which is basically the ratio of the concentration in the monitor B divided by the ratio of concentration in the monitor A times 100%. So if this is less than 5%, then it's doing better than N95. So if we look at that, so commercial N95 masks were doing really well. Charged and neutral means the aerosol particles we created with the mist, were they charged or were they neutral? So we did it with water and we did it with salt water because that is the typical way these tests are conducted. And you could see a measurable difference even with the crude PM2.5 monitors, but both of them were below 5%. If it is above 5%, then the N95 test has failed. For surgical masks, it clearly failed. So we had, for these surgical masks, you have no tape around the mask, unlike N95 respirator, which gives you a tight fit. So that makes a lot of difference. Without a tape, you are close to 40 to 50% penetration. That means 40 to 50% of the particles are going through, even if you have your mouth covered. But with it taped, you come down to somewhere between 10 to 15%. It's not N95, but still better. Then we have the materials we had created. So we had the polymeric fabric. Before it was electrocharged, so non-electrocharged layer and electrocharged layer. And tests are conducted at two flow rates, 30 and 85 liters per minute, to simulate walking and running. So when we did that, the polypropylene failed. The polypropylene, polystyrene failed at the 30 liter and 85 liter per minute mark, but it came close on the electrocharged part. This is the, these are polypropylene and these are polypropylene polystyrene. So here we did the non-electrocharged and electrocharged at different flow rates, and here we had the aerosol particles, charged and uncharged. And the best tests came out here finally for the polypropylene polystyrene mix, which went below the N95 standard. So that was the one we finally stuck with. And then we also tested the penetration for brand new N95, and then if you discharge it by soaking it in alcohol and recharging it, what happens then? And also the surgical mask that is uncharged and charged. And finally, we reconfirmed what we had looked at, what we had discovered for the cloth mask, that the ions, that they were getting charged because of ion adsorption, but they were getting desorbed, and as it is, then the filtration efficiency was also suffering over time. It was decaying with the charges. So that is what we figured out. I won't bore you any further with that. So I have basically condensed some 50 pages of material spread out over 2 papers that we published into the last 40 minutes. I want to leave a lot of time for questions, but before that I want to acknowledge a lot of people. This couldn't have been possible without help from so many people. So as I said earlier, I first learned of the cotton candy method from a passing remark by my postdoctoral mentor, L. Mahadevan at Harvard. Shankar Ghosh, my good friend and a faculty at TIFR India, was the first to suggest use of commercial PM 2.5 monitors for filtration. Sachin Velankar, whom I met as a young assistant professor when I was a student at University of Pittsburgh, and he's a polymer expert, made several critical suggestions on the polymer material characteristics and critical reading of the manuscript. This work was supported by OIST Graduate University, and I'm particularly grateful to Peter because when we did this work, I requested him that we will not file a patent for it. And he was most gracious to give permission immediately. And the work was taken up by several groups all over the world. I have lost count of the various groups. I do know my former postdoc, Florine Paras, took it up at the French Aerospace Labs, and Airbus Industries had a group going with it. There were groups in Indonesia, Brazil, in Africa, Asia, all over the world. Finally, many people at OIST helped me get this work done on time. Here in DC as head of the engineering section, Ishizu-san, who hopefully is here, and Hyun-Bin Kang, she did the scanning electron microscopy. Hyun-Bin did the FTIR studies. Tomomi Okubo, Andrew Scott, Michael Cooper, Chris Wu, Lucy Dickey, Danny LNB, all from CPR, helped with the web pages. I understand, I learned much later that there was actually a huge flow of traffic when the web page went up on the OIST website, and with the efforts of the CPR in spreading the gospel, so to speak. And then Bruno Humble, Paolo, and Shinya from the imaging section, they helped with the confocal microscopy, and that work I have not shown it. In fact, it's going to be future work. This is not done because nobody really understands how the N95 filtration actually works. And I have one hypothesis which I would like to start with. I don't think it will be, most likely it won't be right, but it's a starting point. And then finally, my advisor, my late advisor from Pittsburgh, and my postdoctoral advisor from Los Alamos, and my postdoctoral advisor from Harvard. They deserve special mention because they gave me a lot of freedom to explore, and what little I know, I owe to them, and my style is in large measure an amalgamation of their individual styles. If you look at their work, you will see mine is a variation on their theme. It's not unique in any way. And finally, the enigmatic title, well, those of you who are Tolkien fans like me know where it comes from. It comes from a poem in The Lord of the Rings. All that is gold does not glitter, not all those who wander are lost. The old that is strong does not wither, deep roots are not reached by the frost. So I'm a big Tolkien fan, and these are the topics I have studied. The ones in black are problems I have studied. The ones in blue are either ongoing or future topics I hope to take up, plan to take up. So the craziness is not done yet. And I'll end with yet another quote from Tolkien, which is, and whether then I cannot say, it's a line from another poem. The road goes ever on and on, down from the door where it began, and now far ahead the road has gone, and I must follow if I can. Pursuing with eager feet until it meets some larger way where many paths and errands meet, and till then I cannot see. So I hope I'm just getting warmed up. There are another 24 years before I retire. And before I stop, there's the final nonlinearity from Venice. So this is Antonio Vivaldi, Il Preteroso, the Red Priest, right? Now, many people, the reason I'm explaining this through this story is many people find my style confusing. And as Peter pointed out, I call it doesn't matter physics. Now, it's customary to quote Feynman, who, because if it's a Feynman quote, it must be right, it's kosher. And he said, if you really have something important to say, then it doesn't matter what you work on. So that is Feynman's quote, I'm not Feynman. So I say, I work on doesn't matter physics because whatever I work on doesn't matter to me. But I don't consider myself unique in any way. There are many people like me who have taken this path. There are pros and cons to it. I'm happy to explain them if you choose to ask me. But I wanted to take this story not of a character you know, but specifically of a character you don't know. And this is the story of Antonio Vivaldi in the 18th century Venice, who trained orphan girls known as the Figlie del Coro at the Ospedale della Pieta. This is a painting from the National Gallery of Art in Washington, D.C., and when it appeared there, nobody knew of these ladies. Even today, I bet you most of you may not have heard of the Figlie del Coro, which means daughters of the choir. The Ospedale della Pieta was a charity institution that used to take in orphan girls left at the scaffetta, a small drawer where if the baby could fit in, then the Ospedale would accept them. And they had a quasi-monastic life, but they had musical training from people like Vivaldi. And the system of the modern orchestra goes back to the Figlie del Coro. The concerto goes back to them. Vivaldi composed 140 concertos for the Figlie del Coro, 28 of them for one specific member, Anna Maria della Pieta. She was born because she had no family, she was an orphan, so she came to be known as Anna Maria della Pieta. But by the time she passed away from this world, she went by different names at different stages. Anna Maria del Violino, Anna Maria del Teorbo, Anna Maria del mandolin. Because she could play all these instruments. This was a time in the musical progression of Venice when a lot of experimentation was going on. And these were the rock stars of the musical scene in Europe at that time. And yet, most of us have not heard of them. Maybe because they were women, maybe because they were orphans, maybe because Napoleon's troops literally threw out their books and records when they invaded Venice in 1787. But the fact that he is famous because he had a chance to experiment with them deserves a mention for them too. But the reason they made him so famous is because they could play any instrument. So there was one, Maddalena della Pieta, who she was a soprano, and in between, during the intermission, she would come and play a solo. There was another lady, Pellegrina, who was trained in violin, harpsichord, oboe, and Vivaldi wrote concertos on the oboe for her, but at the age of 60, she lost her teeth. She could no longer play the oboe, and then she played the violin again. So, there are people who did that, and yet we haven't heard of them, right? So, I'll leave you with one final example, because we come from Japan. Anybody know who this person is? His name is Yokoi Gunpei. Ring a bell? He is responsible for the electronic gaming industry. He was a one-man department who used to maintain the Hanafuda card machines for Nintendo, before Nintendo became famous for what it is. And he used to make games during his spare time, which the chairman of Nintendo saw, and the rest is history. I will not tell you his story. It's all in this book. But what I have explained in the last 40-45 minutes is basically what he set down in this book as lateral thinking with seasoned technology. That is, you take mature technology, just as I did, microwaves, cotton candy machines, and ask what can you do with it that is different from the original use it was intended for. So even there I'm not unique. Okay? There are these people who have done this before time and time again. So let me stop there and take questions. Thank you so much.
Well, thank you so much, Mahesh, for that tour de force. And I was wondering when I was sitting at the end how I can bridge from the gaming industry to the violins, to Vivaldi, to your PhD advisors. I think there's really only one thing. It's creativity. So what you have taught us is to be creative. And that creativity really emerged from your talk. And, you know, I could have never imagined what kind of science you can do using a drill and a beer can, an empty beer can, thanks God. So, in any case, Mahesh, are there questions or comments that you would want to bring forward or ask Mahesh?
If you have any questions about any of these topics, I'm happy to answer.
Mahesh, very beautiful talk. I have a question related to so you mentioned the TSI based in Minnesota. That's the company also making micro PIV setup, the same company. And so for their standardized test related to the filtration percentage, is it dependent on the charges of the particles and also particle size?
It does depend upon the particle size, but their machines do not measure the charges.
Okay.
So that you have to do separate.
Mm-hmm, mm-hmm. And what about the types of particles? And everything you tested here, they're rigid. What about deformable particles, like a virus particles and such?
So we did actually do it with aerosol particles, basically water. We also did it with polystyrene beads. So we did both deformable particles as well as rigid particles. One thing I should mention that is very different between the filtration tests we performed and what TSI machines do. They give you the distribution of the bioaerosol particles by their size. There was no way for us to measure the size. Ours was a binary measurement. Is there a particle or is there not?
Okay. Okay, thank you. I just want to make one remark. Back in May 2020, so my unit with the free unit, we're also making face shields. And we encountered a lot of kind of supply chain problem. And then I heard about Mahesh was making N95. So one day I saw Mahesh in the hallway. I said, "Do you have a mask for me?" And Mahesh was like, "No, it's
They were all gone.
Yes, it's a black market." And the next day I saw Milan was wearing one. I was very jealous.
But I gave masks to Milan, but they were not the masks I made. So what happened? So I had kept some masks, but the postal worker came to deliver the PM 2.5 monitor, and he did not have a mask. So I gave him what I had set aside for Milan, and I gave Milan the mask I had set aside for myself. And then I went back and made more masks for myself. But Milan also gave me cookies.
Any more? I understand there's coffee or some cookies outside, so however, yes, come in, go ahead, wait.
Regarding the location of Okinawa,
I think it's
kind. Regarding the location of Okinawa, what kind of creative potential do you see here locally? Low-hanging fruit. Can I ask such a question?
You can ask any question.
well,
Because
you
we're
can
here,
use an
right?
Orion beer can.
I'll give you an example. So I heard once that two brothers, after the Second World War, came across the pile of Coca-Cola bottles that were entering the trash, and they wondered what could we do with them, and that was the birth of the Ryukyu glass industry. Right? So one of the ideas I had after this attempt was, what if I could take the discarded computers, laptop, monitors, etc., and ask myself, how could I reuse, repurpose, or recycle them? I don't know, but the standard way it is done is basically you send them to some chemical processing facility. But I come from a lab where we did not have much funding. It was just me and my advisor. We used to make stuff by ourselves to do our measurements. So that culture has sort of carried on. So you actually find the best Fresnel lenses in computer monitors. You get the best Gaussian diffusers in computer monitors, and they're the cheapest also and the best engineered ones that you would find for that size. Even Thor Labs or Newport could supply that sizes. You get Peltier modules that actively cool down the microprocessors, which you could convert into microscope thermal control stages. You could take the cameras from your smartphones and your laptop monitors and turn them to look at as sky images to do solar photovoltaic measurements. So there is a scope for a startup with reuse, recycle, repurpose. And there is Okinawa Kosen, not far from here, and they are bright young students who have just the right amount of training to take the idea. I'm 46 years old. I'm considered a dinosaur in Silicon Valley. I'm not good enough to create a startup. But there is a lot of scope for creativity in Okinawa. There's a lot that comes from this island. Another example I'll give you is in the north of this island, there's an artist by the name of Ichiro Kikuta who lives in the village of Ada. You have his bureau at your place. So he was the first artist to showcase his work at OIST in the first year after my arrival. And in the video that CPR created, he makes a curious remark. He says, these paper partition screens are good at humidity regulation as well as thermal regulation. And so I took it up upon that, and I visited him, and with help from Ayano, the backbone of my group, RUA for my group, and she helped with the translation. He gave us a bunch of handmade Japanese papers, washi, and we tested them in the lab, and he was right. And there is no theory to explain the effect. And it happens because of several layers of these paper being stacked up, which basically leads to, paper is a peculiar material. It absorbs vapor molecules, and then it starts puffing up. And because of that, the pores close in. So this is what in applied mathematics is known as the moving boundary value problem. So the next layer is ready to take new vapor molecules, but they are unable to pass through. So you have to wait for them to diffuse to the other side and then go. So this delays the propagation of humidity from outside to inside the house. So somehow the Japanese and the Okinawan people had figured it out by trial and error. But we scientists have to give the empirical quantitative tests and produce a theory out of it. So my hope is one of my group members can help me work with Kikuta sensei to provide the explanation. So there are examples. I can only go through examples because science itself proceeds through examples.
Another example of his enormous creativity, the way to bridge things, and I wish you luck in doing many more things. He is the man who can translate it into products and hopefully companies. So before we go, you've seen this in the first slide from Amy. This is like a recognition of today's talk. And when Amy asked me about a nice sentence for you, I just figured, to Mahesh, who can make sense out of chaos.